Good morning. Happy New Year. Happy New Year. It's the new year. We're going to do more math. So let's get started. Sharing the screen. Where did you go, screen? Oh, goodness gracious. There you are. All right. Here's our screen. We're going to do non-constant rates. This is the thing. It'll have this video will be right here later, which is the only thing that should look differently here. And we have our PDF. We have our non-constant rates right here. We're going to talk more about skateboarding and stuff like that. This should be pretty straightforward. This is about non-constant rates. The bottom line is constant rate, something we learned earlier, that's always going to make a straight line. If it's flat like this, it means it's a constant rate of nothing. They're not going up, not going down, nothing is happening. It's going like this, that means it's a constant positive rate. Oh, the screen might be backwards. As it goes to the right, it should go up. That's a positive rate. As it goes to the right, if it goes down, that's a negative rate. And we talked about that. The bigger the number, the steeper the line, the faster the rate, the same thing, okay? You can have a really steep negative rate, which means something's going down really fast, a really large number for the rate, and same thing for positive. All right, the constant rates, non-constant rates are changing. Constant means to not change, non-constant means to not change. So what we're talking about is something, instead of the car is traveling at 20 miles an hour for 3 hours, how far did it go? Well, do cars really stay the same speed all the time? No. In real life, things change speed and change direction and change all sorts of things. And so that is called a non-constant rate. I know you could just say changing. That's really what non-constant means, changing. Okay, so that's the name of the game here. And I just realized I've not actually opened up Agile Mind. Sorry to waste a couple minutes of time. Here we are. That. Need to capitalize. There. Okay. And just remember, you can do this too. You can log in with your students' information. I made a video on it. It's in the playlist. So use it if you want to go into here. But this is just, I'm going to go through it a bit. And honestly, some of these things, rates that are not constant, some of these things take a while. They're just, I like the book for info. It's got some cool things in it, but also can take a while and not be terribly helpful. So it's up to you if you want to use it. Okay, we're back at this. I can't remember the skateboarder's name. Does it tell us? It doesn't. Oh, well, we'll just call him Fred. Fred is a skateboarder, and Fred skates back and forth, and we keep track of how far he is from the motion detector on the left side of the screen. And look at that. He starts 4 feet away. He moves until he's about 1 foot away. Then he goes up farther away until he's just over 7 feet away. And then he comes back. He's moving slowly, and he moves faster and faster and faster toward the motion detector. That's what we're talking about here. That's what they're referring to in the assignment. So how did you move the skateboarder to create the different curved shapes? That's what we're going to do. I'll show you in here. You can definitely do this. You can mess around with it. So we want to make this curved shape. Well, the first thing we want to ask is, where does he start? Where does he start? Well, at the start, that's to the left side. That's when 0 seconds have gone by. So this is at the start. He is right. Is he close to or far away from our motion detector? Well, he's not 8 feet away. He's not 6. He's at 0 feet away. So he starts at the motion detector. And the entire time he's moving away from it, right? Now what we've said is a faster rate. If something's happening faster, it's going to be a steeper line. So notice it's a very not steep line. It's a very shallow curve to the line until it gets steeper and steeper and steeper and steeper, right? So that makes me think he's going to start out moving slowly. And as he gets further away, he's moving faster and faster and faster so that the distance gets bigger at a faster rate. So let's try that. He starts here, starts out really slow, faster and faster and faster. Looks like I went too fast, didn't I? But you can see he starts out slow and goes faster and faster and faster. So let's see if we can do that again. Slowly. That's really hard to do perfectly. And you'll find that in real life, things don't make perfect lines like this. They tend to wobble a little. Oh yeah, oh, almost. But you get the point. He starts out, he's barely moving at all, and as he gets further to the right, as time goes by, he moves faster and faster away from the camera. So that's the type of thing we're discussing here. That's all for these types of problems. We're not going to get too mathy with this because honestly, the math that you need, you haven't learned yet. So most of this is going to be answer in words, and that's okay. This right here, it looks like an exponential curve. So yeah, that's interesting. And we'll talk about exponential curves in this book, but not too much. So they start at the motion detector. We'll say right next to it, because that's better English. They begin by barely moving at all. As time goes by, they speed. They move faster and faster away from a motion detector. And that's all we're talking about here. We got a motion detector. They're barely moving at all. Notice, in the first 5 seconds, they only move about 1 foot away. But by the 6th second, they're almost 2 feet away. By the 8th second, they're 4 feet away. So in between seconds 6 and 8, they move more than in the first 6 seconds combined. If you take a look at how high up this graph goes. In 9 and 10, they move almost twice as far as 7 and 8, or 6 and 8, whatever. It depends on how you're counting your seconds. But you can see the line moves up. The distance changes by more as you go to the right, as time goes by. And that's what's going on. Notice in this, speed is steepness of the line. Speed going up is him moving fast. If it's going up, he's moving away from the motion detector. If it's going down, he's moving toward. This is stuff from an earlier assignment too, so hopefully it looks familiar to you. How do you move the skateboarder to create an upside down U of this graph? How is this movement different than in the last example? Well, at the beginning, does he start the same? He still starts at the beginning at 0 feet away. So we know that he's going to start, but he's also going to end where he started. So he's going to move away from it, then toward it until he gets back to where he started. So unlike the first one, he starts and ends at the motion detector. The first one, he starts at the motion detector, but at the end, he's far away from it. He's 8 feet away on the other end of the, whatever, the skate park. It's a very small skate park too, only 8 feet. All right, the other thing we notice is the steepness of the line. It starts out really steep and then gets shallower and shallower and shallower. And then it gets steeper and steeper and steeper and steeper until it's really steep again. So that means that speed-wise, you should start out going really fast and slower and slower and slower and slower and stop, because when it's level, he's not moving at all. And then start moving back slowly, slowly, faster, 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 faster until he's going really fast. So let's see if we can make that happen. Let's see what they said for their answer, just for the record. The graph is curved, which means the skateboarder is not moving at a constant rate. That's true. Curved lines means they're changing speed or something is changing. A curved line always has something that's changing. This graph shows the distance is increasing. Yes, that's true. To match the curve, you start moving away slowly and then you gradually increase speed. That's what we said. Perfect. Now consider this graph. Okay, let's try to make this graph now. It's going to be great. Here we go. It's going to be perfect. Uh-oh. Okay, well, that was terrible because I got mixed up. We're starting there. We're going to go fast. Oof, this is harder one, isn't it? All right. That's not great. You can see I'm matching it pretty well, but I will tell you this is not a very realistic graph. Nope. So this graph right here, I will say, we've talked about this in our previous assignment on skateboarders. This graph is virtually impossible. And the reason that is he starts out going incredibly fast. And you will find, if you study science, you'll find that things don't start out moving very, very fast unless you got it in the middle of time. Like something must have already been happening. He has to start out going like 20 miles an hour, which is not really terribly possible. Okay, but why won't it let me restart? There we are. Okay, this time it's going to go. That's about as good as I'm going to get. But see, it's really hard to line up perfectly with the circle. This is a circle, by the way. And technically, if this is a circle, that means he starts out going almost infinitely fast, which is why it's very hard to be going up straight perfectly with at the beginning and the end. It's almost impossible. In fact, in real life, this could never happen. You can't start out going this fast because of inertia. Inertia says, no, you have to kind of gradually get into a speed. You can't suddenly be going 20 miles an hour. It's impossible. Okay, so that's an interesting thing. If you guys remember the word inertia, it's a useful thing to know about in life. It actually affects our life a lot. Okay, so what's going on? They, let's see, start and end at the same point. That is one way that this is different from the last. Oh, actually that's differences. They start and end at the same point. They start out fast instead of barely moving. Much like the first bit where it says they start and end at the same point. In order to start and end at the same point, they must turn around and go back the other direction. They go one direction, they turn around and go the other direction. That did not happen the last time. They turn around and go in the opposite direction. There's a lot of stuff we can figure out about things from just a graph. That's why we learn to read them. Okay, how did we do this? They start moving very fast from the motion detector. They gradually slow down. Why did I capitalize gradually? I don't know. Slow down, and they stop. When did they stop? They stop about halfway, which is 5 seconds. Stopping after 5 seconds. they begin slowly to move toward the motion detector. Speeding up as they go. That's good enough. All right, so those are some answers that we just talked through and I showed you in the video. All right, now I got this one. Complete the statements to describe the shape of the graph and it relates to his speed. Okay, we have A, B, C, and D. Notice A, the distance is getting larger, which means during A, the skateboarder is moving away. The distance is not changing, which means B, the skateboard is not moving away from or toward the motion detector. C means it's moving toward because it's getting smaller. The distance between the skateboarder and the motion detector is getting smaller, which means he's moving toward it. And finally, D, he's moving away again because it's going up. But notice it's curving, so he's not moving at a constant rate. Okay. So segment A is, which one's horizontal? Well, horizon is the same direction as horizontal because that's where we get the word horizon and horizontal from. They mean this, they come from the same root. So we want B. B is horizontal because it goes horizontally, which means the skateboarder is, we could say not moving, we could say stationary. Oh, we want to, they've got it right here. What are we going to say? We're going to say still, since that's what they want us to write in. Still means to not be moving. The skateboarder is moving something during segment A and C. Moving constant. And C. Segments, what all show. Okay, so I know this. Which ones all show? 1, 2, 3 of them all show. We talked about that. A, B, and C all show a constant rate. We're going to come back to the middle one there. That's confusing. Because they're all straight lines. Straight line, constant rate, every time for the rest of your life. The speed of the skateboarder at the beginning of D is, okay, the speed is faster or slower than at the beginning. When it starts here, is it going faster, or when it ends, is it going faster? Well, looking at the steepness of the line, the rate has to do with how steep the line is. The steepness of the line is really steep at the end, and really not very steep at the beginning. So this is slow, that's fast. That's what we're looking at. So the speed of the skateboarder, it's slower at the beginning than the speed at the end. The speed at the beginning is slower than the speed at the end. Let's see what I'm missing here. The skateboarder is moving faster during segment A than segment C. That makes sense. That's the only one left. And it's true. See, this is steeper, so it's faster. This is shallower. This is not as steep, so it's not as fast. That's what we're keeping track of in this graph when we look at steepness, is speed. So slow, faster. There. I might as well make constant be that. And that's it. Looks like we never use constant, non-constant. That's okay. Wait. Yeah, we use B twice. That's perfectly okay. Tricky. Consider this graph. Here's Terrence. Oh, that's right. That's the skateboarder's name. Okay, so Terrence starts out 2 feet away, moves away until Terrence is at 9 feet away, and then starts moving back toward until Terrence is 7 feet away. Okay, we're going to consider that. Well, that was easy. We did A, part 4. Now we're going to do A. We're going to make a table. Okay, let's make a table. What are the two things I need to keep track of in my table? Well, the good news is they're up on the graph. It's very important to realize tables are just another way to show the same exact information. So if I look at this table, it should keep track of, well, distance and time. Traditionally, often, we like to put this guy first, because if you remember, this is our independent variable, our dependent variable, and usually we like to know the independent first since it affects what the dependent does usually. So time, distance, like so. Boom, there, okay. So how many times are there? There's 1 second, 2 seconds, 3, 4, 5, 6, 7, 8, 9. I'll let you go up to 7 since it doesn't fit. If you want to keep going to 10, go for it. Okay, so, what did I just do? Distance. Oh, we forgot 0. 0. Okay, at 0 seconds, where is Terrence? Terrence at 0 seconds is 2 feet away. At 1 second, Terrence is 3 feet away. Now notice, at 2 seconds, Terrence is 5 feet away. It looks like that one works. Let's do that one. Let's say 5 feet away. Now, notice they didn't put a dot there. Now, actually, yeah, we are not going to use it too, and here's why. We don't know exactly where that is. They did not mark it carefully. Our table has 1, 2, 3, 4, 5, 6 points in it, so we're not going to use all of the 10 seconds. Now, I could guess that this is about 5 feet, but since there's no dot there and there's no point marking it, that's just a guess. And I'd rather be certain about things. So I'm going to use the information that they gave me very clearly. So I'm going to skip second 2, and I'm going to write second 3. I know that I didn't do that initially, but sorry, gosh. Okay, so 3 seconds, 7 feet. 3 seconds, 7 feet. So after 3 seconds, they're 7 feet away. And 4 seconds. Again, 4 is not marked, is it? It looks like 8.5, maybe. Do I want to guess that? No, I'm just going to use the information they gave me. So now we're jumping to 5 seconds. 5 seconds is 9 feet. You can see that. 6 seconds, not there. 7 seconds, not there. 8 seconds is though, and so is 10. So at 8 seconds, we're at 8 feet. Weird. It changed size. 8 seconds, 8 feet. 10 seconds, 7 feet. Now I've got a table. So I used all of the information that they gave me clearly. I did not guess these ones in the middle. Why would I do that? I'd rather stick with what they gave me that's very clear, that has points marked. Find Terrence's average rate from 0 to 1 second. Okay, now average rate. Let's see if they have some information on that before I just tell you what to do. Yeah, we did that. Average rate, okay. So average rate is what I'm saying, like say I spend, let's talk about spending on average. So if I go to the store and sometimes I spend $2 and sometimes I spend $4, the average is going to be somewhere around 3 because I don't always spend $4, I don't always spend $2, and those even out where, you know, it's about $3 every time, even though sometimes I spend more and sometimes I spend less. That's what we're talking about when we say an average rate. So it can be changing, but on average, where does it end up? So that's what we're going to do with speed. So notice from 0 to 1, he moves about 1 foot in 1 second. But here, he's moving 1, 2, 3, 4 feet in 2 seconds. So that's about 2 feet in 1 second, and so on and so forth. So what we're trying to figure out is how many feet overall are they moving per 1 second? So that's actually kind of like finding the slope of a straight line. It's the same type of reasoning. And actually, when you go to calculus, not that you're going to do calculus in my class, but that's the goal, to try to find the slope of lines like this. Even though they're changing, you can find an average slope, and that's helpful to us. And you can actually be more specific later in math. Okay, what was Terrence's average rate during the activity from 3 to 5 seconds, 5 to 8 seconds, 8 to 10 seconds? Let's take a look back at this. So we want to know from 0 to 1 second. 0 to 1 second. So how many feet was he moving in that 1 second? Well, in that 1 second, he moved 1 foot. Now notice, at the beginning, he's moving slower. At the end, he's moving faster, but overall, it evens out to 1 foot in 1 second. So that's 1 foot per second. That's the average speed. 1 foot per 1 second. Or 1 foot per second. Okay, what about from 1 to 3 seconds? Let's take a look at 1 to 3 seconds. Well, if I take a look at 1 to 3 seconds up here, from 1 to 3, he moves, that's 2 seconds. And that's 1, 2, 3, 4 feet. That's 4 feet in 2 seconds. Can I make that simpler? Now we're doing rates, right? In rates, we take, what was it? The independent divided by the dependent, right? No, sorry, I said that backwards. The dependent divided by the independent. We did that. That's in an old assignment. So, dependent divided by independent. Let's see, that is 4 feet divided by 2 seconds. 4 divided by 2 feet divided by 2 seconds. Well, I can simplify that fraction. That's 2 feet per second. So what we're finding out, just to make this completely clear, this is fancy math, and I'm typing it so it looks ugly, and I'm sorry about that. But what we're saying is, from here to here, he starts out a little faster and slows down a tiny bit by the end, but overall, he's going 2 feet, sorry, in 2 seconds, he's going 4 feet. That's what we're saying. That's all. That's what this boils down to. So, in other words, on average, he's going every 1 second, he's going 2 feet. That's what we're saying. Okay? In order to go 4 feet in 2 seconds, he's going about 2 feet every 1 second. Don't overthink this. It is pretty straightforward. All right, that's what's going on. And I was doing it by simplifying a fraction down here. It doesn't look much like a fraction because I typed it. During the remaining of each intervals. Okay, so let's figure this out. Next interval is from here to here. That's what it would look like if I just went straight with a constant rate. He starts out going faster and then slows down, but on average, he's going about 2 feet in 2 seconds. So how many feet is that in 1 second? I'll do that in green real fast. Well, that's 1 foot in 1 second. 1 foot in 1 second. He's going 1 foot per second. That's the same speed as down here. On average, this has about the same speed as that down there. So from seconds 3 to 5, he's going about 1 foot per second. During seconds 3 through 5, they are traveling about 1 foot per second. Okay, let's move on to the next one. Okay, well, now we're going to go from here to here. Notice this is a lot shallower of a line. That's okay. Let's see, so it's taking them 3 seconds to go 1 foot. So how many feet is that in 1 second? Well, if I were going to divide it evenly, if this were a straight line, which is what we do when we make an average, even though he starts out going really slow and speeds up a tiny bit more as he's going, technically we just want to know if I spaced it out evenly over those 3 seconds, if I took the average, how far is that per 1 second? Well, that's to get 1 full foot in 3 seconds, I have to go 1/3 of that foot every second. And that's the speed, 1/3 of a foot per second. It's a fraction of this guy and that guy. Every time the answer is a fraction of the left, or the up and down divided by right to left. That's also how we find slope. It's the same thing. So we got 1/3. So during seconds 5 through 8. And I'm going to go like this, 1/3 of a foot per second. All right, last one is during seconds 8 through 10. They travel an average of, oh goodness, oops, wrong one. Oops, wrong one again. I just need to go up here. All right. So from 8 to 10, think about it. Come up with your own answer. This is almost a straight line. He starts out a little bit fast and then slows down, but on average, it would, if I was averaging it, it would be just a straight line. And that straight line goes down 1 foot in 2 seconds. If I switch colors, that means in 1 second, the first second would be half a foot. The second would be half a foot. So each of these 2 seconds, he goes about 1/2 foot toward the motion detector. So per 1 second, he's going 1/2 of a foot. That's another fraction of 1 and 2. It's always a fraction of up and down divided by right to left. Rise over run. Rise over run. That's what people mean when they say rise over run. This is the slope. What we're finding is the slope. So as we go further on, we talk about slope, we're still talking about the same thing. An average of 1/2 of a foot per second. Okay. Great. There's that. Now that you've found the average rate, what do these rates tell you about how Terrence skated? Explain these differences in context of the situation. Okay, let's take a look at this. So, he starts out fast. He goes at a general speed, at a nearly constant speed right here, doesn't he? But then he slows down. But on average, I could figure out on average how fast he went. And on average, how fast he went this way. On average, he was going faster away than he was when he was going back, right? During the first 5 seconds, he traveled how far? From 2 all the way up to 9, that's 7 feet. So in 5 seconds, he traveled 7 feet. But in the next 5 seconds, he traveled 2 feet, right? So clearly, he's traveling way faster on average when he's going away than he was going toward. And you can see that because he doesn't get back to where he started, does he? He's still 5 feet away from where he started when he ends. So there's a lot of stuff you can figure out from a graph. Reading graphs is a very good skill. What do these rates tell about how he skated? Well, on average, Terence skated much faster away from the motion detector during the first 5 seconds. Oops. Yeah. That's what we could say. There are a lot of other things you can say if you want to say them, but that's just kind of a fishing question anyway. Okay, here's another graph showing Terence's movement. This right here is a very common graph. This is a parabola. Find the average rate of change between each of the points. Calculate the rate of change. So again, we're just finding the average. So remember, average is always the distance up and down divided by the distance to the right. Rise over run. Rise over run. A lot of people say that, but that's just a fancy way to, what that is just how far it goes up or down divided by how far it goes to the right. It's also how much y changes divided by how much x changes. Y, x. So this is 2, and this is 3. So what I'm going to do is, that's the numbers I use to find the average every time. And what we're doing is we're just kind of ignoring the curve. We're saying, well, on average though, if this was a straight line, what would that be? So we're just kind of turning this the non-constant line into a constant and saying, well, if I needed to get from here to here, and I just wanted a straight line, what would that constant speed be? Well, that's what we're doing. That's how we find an average speed or an average whatever from a curved graph like this. So now I have 1 and 2. The other side's going to be the same. 1 and 2. Can you see how this is a mirror image of itself? 3 and 2. 1 and 2. Like so. This graph is a mirror image like this on left and right. And so once I find the left side, I have the same answer for the right side. The only difference is one's going down, one's going up. So this one's going to be down 3. This one's going to be down 2. So the rates over here are going to be negative. The rates over here are going to be positive. So find the average rate between each of the points. Okay, so let's see. I'm going to make a list real fast. I'm going to say from -1, no. It's 1, 6 to 3, 3. The rate, average rate. From 3, 3 to 5, 2. from 5, 2. What I'm doing is I'm typing in these points just so you understand what I'm doing. This is the point, or to mark this point is at the point, let me change it to another color. This is the point 1, 6, 1, 6. This point right here is the point 3, 3, 3, 3. So if I want to talk about the rate between these 2 points, I need to say those 2 points, and there they are right there. So what I'm saying is this first section, I'm going to find the slope and put it right here. Okay, so that's what's going on. Just so you understand. I'll leave these guys up here, but I don't want to have too much writing down here. Okay, back to writing. So I'm making my 1, 2, 3, 4 points here. My 4 sections between those 5 points, technically. 5, 2, 2, 7, 7, 3, 7, 3. Okay, from 0.73, 73 to 9.6, 9.6. The average rate is, and there we are. We got our average rates. Pretty exciting stuff. Well, I haven't written them in yet. I'm going to write them in with actual numbers because it's easier to write fractions that way. So notice we had, it goes down 3 and over 2. That is the rate. That's the rate. That's all it is. We're just making a fraction of those 2 numbers. So if it goes down 3 and over 2, that's down 3, that's -3. And over 2, which is down 1.5 per second. So I could say, or -1.5 feet per second. And there we are. Now the next one, it goes down 1 and over 2. So for every 2 seconds, it goes 1 foot, or that's going to be half a foot every second. We did that in the last one. But all I really have to do is make a fraction of them. Down 1, and over 2. That's down 1, over 2. Notice I put negative for the down parts. That's important because, yeah, or 0.5 feet per, oops, -0.5, -0.5 feet per second. There you go. And the next ones are mirror images. So instead of going down, they're going up. So they should be exactly the same fractions, only without the negative. So instead of going down 1, it's going up 1. Instead of going down 3, it's going up 3. And there you go. Those are our answers. You can write these without negatives as well if you'd like. But I'm just in a hurry, so there you go. When is Terrence moving the fastest? Well, at the beginning and the end, because that's when it's steep. Steep means fast. Since a steeper line means he is moving faster, Terrence is moving fastest at the beginning and end. What is Terrence's average rate change between 3 and 7 seconds. What does this rate mean? 3 and 7 seconds. Let's find 3 and 7. 3 is right here, 7 is right here. So what we're talking about when we say 3 and 7, we're talking about between here and here. How much does he move between those 2 points? If I connect them, he starts out moving toward the motion detector, and then he starts moving away from the motion detector, and he ends up exactly the same distance away, right? So what is that average speed? Well, to find an average speed, you take how far they moved divided by how much time has gone by. So I could take he moved none divided by how much time has gone by. That's 4 seconds. Well, 0 divided by 4, anything, 0 divided by anything is just 0. 0, 0 is 0, 0. How many 4s does it take to make 0? None. So what's that saying? Well, on average, he didn't move at all. Okay, just like with money, if I spend $10 and make $10, it's like I didn't spend or make anything. They cancel each other out. So the distance he moved toward the motion detector and the distance he moved away, they balance each other out. On average, he moved none, 0. Okay, so that's what we're asking now. So on average, Terence did not move at all. That is because the distance moved, the distances he moved in each direction canceled each other out. There. That's what we could say. Oh gosh, we're at the last pages already. Killing it, killing it. Trying not to talk too much these days. Okay, here's another graph that shows Terence's movement while skateboarding. Look at this. He's not moving. Okay, we're gonna finish the statements. A, is he moving constant? Yeah. It is constant because it's not changing. But we could also say change that is 0 because he's not changing at all, is he? So 0 is what I would put there for no change. Section B indicates that it is constant and what? Is the rate going up or down? Well, it's clearly going down, which means we have a negative slope or a negative rate or a negative whatever. So remember, going down means a negative rate, always. As you're going to the right, if the line goes down, it's negative. The only other place that's negative is at E. Okay, section C indicates the rate of change is what? Positive in constant. That's what I would say. D, it's still going up, right? So it's still positive, but now it's curvy. It's no longer constant. It's changing speed as it goes. So it's still positive, but now it's not constant. And E going up or down, it's going down, so that's negative. And it's curvy, so it's not constant. According to the graph, Terence was moving what during the time represented by section B, then during the time represented by section C? Look at B and C. Which one is he moving faster? Now, one of them he's moving in one direction toward the motion detector. The other one he's moving the other direction away from the motion detector, which means that the distance is getting closer, further away. That's what makes the line go up versus down. But speed, if they're just asking about speed, they don't care about whether he's going up or down. They just want to know which like how fast he's going in either direction. And remember, in this case, speed is how steep. It's the rate, right? So it's how steep the line is. Which line is steeper? B is clearly steeper than C. In B, it says it takes him 1 second to go 3 feet. But in C, it takes him like 4 seconds to go 1 foot. Definitely, he's going faster during section B. So it was moving faster during the time represented in section B and in the time, whatever, represented in section C. All right, last page. The graph models a skateboarder's movements in front of a motion detector. Now, you don't have to watch me if you don't want. This is definitely something you could do. Match each description. So when does he stop moving? I'm gonna give you a second. 5, 4, 3, 2, 1. Hopefully you understand. Down means he's moving toward the motion detector. C means he's moving away and the distance is getting larger. B means he's not moving at all because it's not going toward, it's not going away from. He must not be moving. Now, I will say, if you think three-dimensionally, there are other options. He could be moving in a completely different direction. He could be skating in a circle around the motion detector, and then the distance would be changing. But that is not the situation we're describing right here. He's skating back and forth away from and toward. Okay, moved fast at a constant rate. Which of these is constant? 5, 4, 3, 2, 1. If you said that A is constant, you're right, because A is a straight line. Whoa, that's weird. Okay. Okay, he moved away from the motion detector. Which one is he moving away from the motion detector? 5, 4, 3, 2, 1. C, he's moving away from it in C because the distance between him and the motion detector is getting larger. C. And which one is he slowing down during? Well, this one. Sorry, I'm going to have a moment first. 5, 4, 3, 2, 1. We will say that he slowed down in C. In A, he's moving at a constant rate. Constant means not changing. So you can't speed up or slow down. It means you're going the same speed the whole time. That's why the line is straight. Whereas this one, he's going fast. He's not going as fast. The line gets shallower and shallower. It gets less steep, which means he's slowing down. So in C, he slowed down. There you go. Describe how you would move a skateboarder to create this graph. So here's what I'm going to say starts. Movement ends. Those are the things that I want you to discuss in each one. So where does he start? What happens? Where do they end? Okay, so that's your 5 seconds. I'm going to talk now. So he starts close to or far away from. The distance is large. Far away from the motion detector. Okay, that's easy. Movement. Skates forward. Oops. Okay, so he skates toward the motion detector, speeding up right here. Fast, 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 fast. Slows down and stops. Slows down and stops. Skates about the same speed away from the motion detector. Slows down and stops where he began. All right, so that's some answers that might work. I know you could say here he skates a tiny bit past and then turns a tiny bit around and comes right back to where he began or something like that. That's fine. You can be very, very minute, but I'm trying to save time on the video, so I'm stopping with that. Hopefully this stuff makes sense. Remember, straight line means constant rate. Curved line means non-constant rate. Line going up means the rate is positive. Line going down means the rate is negative. Line that's level at any point, even in a curved line, if it's level in the middle, level means it's not moving one way or the other. Those are the things we want to talk about. In this case, we're talking moving, but it could be a temperature. It's not changing up or down. Or it could be money. Your balance is not going up or down. It could be anything, but level means nothing's changing. Positive slope goes up, negative slope goes down. All right, that's it. I'm going to stop sharing this and I'm going to stop this video before I make it any longer.